Under properties of colloidal solutions, we were talking about charge on the colloidal particles. This is responsible for generation of electric potential between two layers which are formed around colloidal particles. Look at this. Let us take the example of AgCl colloidal particles. This is a cluster of AgCl, and imagine you have an excess of KCl added to it. Then the common ion is Cl minus. Cl minus ion gets adsorbed on the cluster of AgCl because it is a common ion. These negative particles which are surrounding the colloidal particle, take them as chloride ions. Now, then this will be a fixed layer of charge around the colloidal particles. Around this, another layer of oppositely charged particles, here there may be K plus ions, which get surrounded. The colloidal particles will be surrounded by two layers of charges. One is the charge of the common ion, and then you have a layer of opposite charge. So there is a potential difference between these two layers, and this potential difference is called as zeta potential. Zeta potential is the difference in the potential between fixed charge layer around the colloidal particles and the diffused layer. Diffused layer is the one which contains ions which have charges opposite to the ions which are immediately surrounding the colloidal particles. These ions can rapidly interchange with the ions present in the solution. That's about zeta potential. This is the electrical double layer, one layer fixed, and this is diffuse layer, and the difference in the potential is described as zeta potential. I would like to add one more point here, that due to this charge on the colloidal particles, they tend to repel each other. Because of this repulsion, they keep away from each other and do not aggregate. This will stabilize the colloidal solution. Otherwise, the particles will just merge, form aggregates, and will fall down as suspension. So what keeps the colloidal particles stable is the presence of adsorbed charged particles on the surface. Under properties of salts, we are discussing properties of salts. Under this, the next one we are going to discuss is colligative properties. Just remember this, as the colloidal particles are large in size, you will have, these are formed due to aggregation of smaller particles. So when compared to true solution, colligative property value of any colloidal solution will be lesser in magnitude. See, the important colligative properties are osmotic pressure, elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure. Take the case of osmotic pressure. Osmotic pressure of a colloidal solution will be relatively very less when compared to the osmotic pressure of a true solution. So colloidal solutions have lesser value of colligative properties when compared to true solutions. Number 3 is Brownian movement. If you see the colloidal solution with the help of microscope, you will find that the particles are moving in a zigzag manner. This zigzag movement of colloidal particles is called as Brownian movement. Zigzag movement of colloidal particles is called as Brownian movement, and we explain it on the basis of this assumption that the particles of dispersion medium will cause constant collision on the walls of the particles of dispersed phase, and due to these uneven collisions, these particles move in a zigzag manner, and this is responsible for stabilization. Also, this gives a stirring effect. The solution is always in a state of stirring. Number 4 is electrophoresis. Colloidal particles, due to their charge, they can carry current. Their ability to carry current is described as electrophoresis. This can be demonstrated using a U-tube. You have a U-tube filled with colloidal solution. Imagine this is a U-tube. Put 2 platinum rods in this, and what you have here is colloidal solution in the U-tube. When you pass current, see, the colloidal particles may carry either positive charge or negative charge. So when you carry current, imagine the colloidal particles are positively charged. So what happens, all the positively charged particles will get collected in this limb, in this tube where you have a anode. So this portion of the U tube will have a true solution and it will be transparent, whereas this portion will become translucent. So this demonstrates that colloidal particles can carry current. Electrophoresis, current carrying capacity of colloidal particles. It is because of the charge carried by the colloidal particles. Number 5. One of the important properties of colloidal solutions is they exhibit what is called as Tyndall effect. This is scattering of light. This property of scattering of light is called as Tyndall effect. See, there are two conditions which must be satisfied for a colloidal solution to exhibit Tyndall effect. See, some colloidal solutions exhibit very weak Tyndall effect, some exhibit very good Tyndall effect. So there are two conditions which have to be satisfied for colloidal solution to exhibit Tyndall effect. Number 1 is particle size, that is size of colloidal particles. Particle size should be comparable with wavelength of light which is being used. This is first condition which must be satisfied. And then the second condition is refractive indices of disperse phase and dispersion medium the refractive indices of disperse phase and dispersion medium should differ considerably. These are the two conditions which must be satisfied for a colloidal solution to exhibit Tyndall effect. So due to Tyndall effect, the light gets scattered, and the blue color of sky is due to Tyndall effect. The blue light of visible light will get scattered and you see the blue sky. The next important property of colloidal solutions is color. They exhibit color. See, this is again a consequence of scattering of light. So color exhibited depends on two things. A, it depends on wavelength of light which is scattered by the colloidal solution, and the next is the direction of viewing. These are the two things which decide the color of colloidal solution. Regarding this wavelength scattered in turn depends upon the size of the colloidal particles. It depends on the size of the colloidal particles. Gold sol appears red. As the particle size increases, it becomes purple, then it becomes blue, and then it ultimately appears golden, its original color. So from here to here, particle size increases. So you can realize that the color of colloidal solution depends on the particle size, which will decide what wavelength gets scattered. So if the particle size of gold sol is very small, then the gold sol will appear red. It may become purple as the particle size increases, then blue, and finally it appears golden. Milk may appear blue or red. It depends upon the direction. If you view through the reflected light, it appears blue. If you view it through the transmitted light, it appears red. Now let us not talk about coagulation. Coagulation means settling of particles of colloidal solution. Settling of particles of colloidal solution is called as coagulation. See, the disperse phase and dispersion medium separate from each other during coagulation. What keeps a colloidal solution stable is the stabilizing ion. The ion which gets adsorbed on the surface of colloidal particles will impart charge, and these colloidal particles of like charges repel each other and they don't aggregate. Now let us see what are the various ways you can coagulate a colloidal solution. Settling of colloidal particles is called as coagulation. I can say coagulation is the opposite or the reverse of peptization. Peptization is transformation of precipitate into colloidal solution, whereas coagulation means transformation of colloidal solution into a precipitate. Now let us look at the methods of coagulation. Number 1 is electrophoresis. I told you what keeps the colloidal solution stabilized is the presence of charges. The colloidal particles are adsorbed by common ions, and these charges will cause repulsion among colloidal particles and they don't aggregate. Now electrophoresis is a process where colloidal particles move towards oppositely charged electrode. When they move towards oppositely charged electrodes, they get discharged. When they get discharged, they can aggregate and in this way coagulate. So electrophoresis can bring about coagulation due to discharge of stabilizing ion. Stabilizing ion gets discharged, loses its charge, and therefore the particles now will not be able to repel each other. They lose their charge, they cannot repel each other and they aggregate. Next, another way you can coagulate is mixing of two oppositely charged salts. If you mix two salts having opposite charges in their colloidal particles, then they can cause mutual coagulation. Let's see. I have a colloidal solution of AgCl having Cl minus adsorbed on the particles. That means it is a negatively charged salt. I have another colloidal solution of AgCl having Ag plus as its coagulating ion. This has Ag plus as its coagulating ion. So we prepared this by adding silver nitrate and KCl. We took excess of AgNO3. In this case, we used excess of KCl. Now, these two colloidal solutions, if I mix them in equimolar ratio, then the stabilizing ion of this and the stabilizing ion of this will combine, and it will lead to formation of a precipitate of AgCl. So, when oppositely charged colloidal solutions are mixed in equimolar ratio, they cause mutual coagulation. This is another method of coagulation. Another method for coagulation is boiling of colloidal solution. This will disturb fixed layer of charge. Due to constant collisions, it increases impact of particles of dispersion medium on the fixed layer, and it will disturb the fixed layer, and in this way it loses charge and gets coagulated. Number 4 is addition of electrolyte. Now consider you have a colloidal solution of AgCl with Cl minus as a stabilizing ion. Now if I add a small amount of AgNO3, this is the electrolyte I am adding, I need it in a very small amount, then what happens is this Ag plus will pick up this Cl minus. When Ag plus picks up Cl minus, this particle now will lose charge and they aggregate to form a precipitate of AgCl. So addition of electrolyte. I will give another example. See, I have a colloidal solution of this type. It's a positively charged species. Here the common ion which got adsorbed on the surface of colloidal particle is Ag plus. Now in order to coagulate this type of colloidal solution, we need electrolyte like KCl, you can use KBr, you can use Ki. Then the Cl minus present in this electrolyte will join with Ag plus and you get again AgCl. So what you have realized in this case is, in the first case the coagulating ion is Ag plus because the colloidal particles are carrying negative charge, and in this case the coagulating ion is Cl minus because the colloidal particles are carrying positive charge. So the coagulating ion will carry opposite charge to the charge which is being carried by the colloidal particle. So in the electrolyte you have two types of ions, cation and anion. If the colloidal particles are anionic, then cation of the electrolyte is responsible for its coagulation. See, what is important is these two should be capable of forming insoluble substance. That is the requirement for this. Now based on this coagulating power, there is a rule called as Hardy-Schulze rule. I will discuss now. Regarding this, there is a rule called as Hardy-Schulze rule, which says that coagulating power is proportional to the valence of coagulating ion. That means as the charge on the coagulating ion, magnitude of charge on the coagulating ion increases, its coagulating power increases. Look at these examples. Coagulating power for cations, it is Fe3 plus greater than Mg2 plus greater than Ag plus. For anions, you can say FeCN6 4 minus is greater than PO4 3 minus, this is greater than SO4 2 minus, this is greater than Cl minus. So you can see as the magnitude of charge decreases, its coagulating power decreases. This is most efficient in coagulating colloidal solution in which colloidal particles carry positive charge, whereas this is most efficient for coagulating colloidal solution where the colloidal particles carry negative charge. Here you should also be familiar with another term which is used in this coagulation by addition of electrolyte, that is flocculation value. See, another name for coagulation is flocculation. You can also call it as precipitation. Precipitation of sol or coagulation or flocculation means the same thing. Now what is flocculation value? It is the number of millimoles of electrolyte, required to coagulate one liter of sol in 2 hours time. Number of millimoles of electrolyte required to coagulate a liter of sol in a duration of 2 hours is called as flocculation value of that electrolyte. And remember, higher flocculation value indicates lesser coagulating power. An electrolyte with high flocculation value indicates that its coagulating power is less. That means the charge carried by the coagulating ion is lower. Another way you can cause coagulation of colloidal solutions is by repeated dialysis. If you do repeated dialysis, you will lose all the stabilizing electrolyte also. The stabilizing ion also is lost from the colloidal solution, and that will cause coagulation of colloidal solution. Repeated dialysis is another way you can cause coagulation of colloidal solutions. That completes coagulation of colloidal solutions. I'll now talk about a brief discussion on protection of colloidal solutions. How can we stabilize colloidal solutions? protection of colloidal solutions. It has been observed that when a lyophilic sol is added to a phobic sol, it offers protection to the lyophobic sol against coagulation upon addition of electrolyte. You know, one of the differences between lyophilic and lyophobic sols is lyophilic sols are more stable, they cannot coagulate so easily, whereas lyophobic sols coagulate very easily upon addition of small amount of electrolyte. See, the reason why lyophilic sols are more stable is due to solvation. Lyophilic sols are solvated, they are surrounded, they are encapsulated by particles of dispersion medium. Lyophilic sols are coagulated, and that is responsible for stabilization of lyophilic sols. Now, if a lyophilic sol is added to a phobic sol, that will create a film, a protective film on the surface of particles of lyophobic sol, and this will lead to their protection against coagulation upon addition of electrolyte. Lyophilic sols protect lyophobic sols. Lyophilic sols protect lyophobic sols. The protective power of lyophilic sol, which is offered to a phobic sol, is expressed in terms of an important term called gold number. Gold number is an index of protective power offered by a lyophilic sol on a phobic sol. It is defined on the basis of this observation. Imagine you have a 10 ml standard gold sol. You have a 10 ml standard gold sol. You are going to add 1 ml 10% NaCl. This is the electrolyte you are going to add to gold sol. Now, this electrolyte will cause coagulation of gold sol. So, before adding this, we will have to add x milligrams of lyophilic sol. The minimum value of x, which can just prevent coagulation of 10 ml gold sol against 1 ml 10% NaCl, is taken as gold number of this lyophilic sol. It can be defined like this: the number of milligrams of lyophilic sol required to protect 10 ml standard gold sol against 1 ml 10% NaCl solution is called gold number of the lyophilic sol. See, it's very easy to make out whether a particular sol is lyophilic or lyophobic. Organic substances generally give rise to lyophilic sol. Gum sol, gelatin, starch sol, protein sol, these are all lyophilic sols, and they can offer protection to lyophobic sols like metal salts or metal hydroxide or metal sulfide salts. That's about gold number. I'll define once again: number of milligrams of a lyophilic sol which can just prevent coagulation of 10 ml standard gold sol upon addition of 1 ml 10% NaCl solution. You'll get some important numericals based on gold number. So, if you remember the definition, you can solve any numerical based on this. See, it is defined for 10 ml gold sol, it is defined for 1 ml 10% NaCl, and the value has to be expressed in milligrams. And one important point you should remember is, higher the gold number of a philic sol, lesser is its protective power. Protective power and gold number are related inversely. Higher gold number indicates lesser protective power.